Let's continue talking about regular languages and regular operations. Particularly, let's talk about intersection and what closure under intersection means. So first, let's remind ourselves what intersection is. If I have two sets, I have two sets A and B, then the intersection is here. Anything that is in both A and B is in the intersection. Okay, I could also have two sets, let's call them A prime and B prime, that do not intersect. Okay, so there's nothing shared between A and B. They have nothing in common. So here we would write A prime intersect B prime is the empty set. There is nothing in the set that is the intersection of A prime and B prime. Whereas up here, for A intersect B, we had something in it, so it's not the empty set. It's something else, some set. Okay, so that's intersection. Let's go back to our example we were using when we were talking about union. So we've got language A is W such that W has an odd number of A's, and B is all strings W such that W has an even number of B's. Okay, so these are our two languages. So if we're looking for A intersect B, this language, it's going to be any strings W such that W has odd number of A's and W has even number of B's, right? In order to be in the intersection of A and B, I have to have both properties. I have to satisfy both conditions. That's why we have the and. Okay, so if we look at our diagram that we drew for union, we notice that things that are in the intersection have these properties. They have an odd number of A's and an even number of B's. So for example, we had the string ABB, we had the string A, we could have any number of other strings. We could have BB, AAA, that might be in the intersection, or that would be in the intersection. So anything that's here, okay, is going to be in the intersection. So continuing to reuse this example, we had created machines MA and MB for languages A and B. Okay, so if we want to create a machine for language L, let me make sure to define that L here is the intersection of A and B. Okay, so that's L. So we want to make machine M for L. Okay, and if we can do that, and if we can show that there's a general do that, then we can show that if I start off with two regular languages and I take their intersection, I'm necessarily going to end up with another regular language. Okay, so that's what we said closure was when we were talking about union. Okay, so how can I do this if I have machine A and machine B? Well, we already showed that if we take the Cartesian product of the states, we make a new machine M that its states are made up of the Cartesian product of the states of machine A and machine B, and then we simulate machine A and machine B simultaneously at the same time on the input string, then we can end up with a machine that does basically what we want, with one big difference between union and intersection. So let's look at that machine. This was the machine that we created. Okay, so what's the big difference? With union and intersection, it's what we're going to accept. So remember, union accepted whenever either language, whenever the string was in either language. When it was in language A or language B, then it should be in language L. Which also meant that if either machine A accepted or machine B accepted, then this new machine M should accept. That was what we did for union. Intersection is different. Intersection says it has to be the case that the string is in language A and it's in language B. So put in machine terms, it means that machine A has to accept and machine B has to accept. Okay, so these are our conditions. It has to be accepted by both machines. So that's all we need to do. We need to determine which final state would represent being accepted by both machines. So let's look back here at our machines A and machine B. So machine A accepted when we had an odd number of A's, and machine B accepted when we had an even number of B's. So that means that machine M should accept when we have an odd number of A's and an even number of B's. Okay, well luckily that's pretty easy to find because of the way we named our states. We're going to accept when we have odd A and even B. So here is our final state. Okay, so that's actually all we need to do, and let's convince ourselves that that's true. Even A, even B can't be a final state because even A means it's not accepted, it's not a string in language A, right? It would not be accepted by machine A, so that can't be a final state. Even A, odd B, well, language A would not, the string would not be in language A because it has an even number of A's instead of an odd number of A's. And that string would also not be in language B because it has an odd number of B's instead of an even number of B's. We can convince ourselves the same thing for odd A, odd B. It wouldn't be in language B because it has an odd number of B's instead of an even number of B's. Okay, so this truly does give us the intersection. Okay, so in general we can use this method given, so we can say here if we have so if we have any regular languages A and B, then we have some machine A such that the language of machine A is A, and we have some machine B, it's a finite automaton, such that the language of machine B is B. Okay, then we can use the product construction to make a finite automaton M from machine A and machine B, and then this means that the language of M, okay, so here we're saying given this particular construction that we're using, the language of M is going to be the language of MA intersect the language of MB, which was A intersect B, which is L. Okay, so we have a machine M for language L, and this means that L is regular. Okay, which means that A intersect B is regular. Okay, so this right here shows closure under intersection, and that's very exciting. Okay, this means if I start off with any two regular languages and I take their intersection, the resulting language is regular. And that's it.